Welcome to The Long Run. This is a podcast for biotech adventurers. I'm your host, Luke Timmerman. Today's guest is John Wilbanks. He's the Chief Commons Officer of Sage Bionetworks. Sage is a nonprofit biomedical research organization founded in Seattle in 2009 by a couple of veterans from Merck. Back then, co-founders Stephen Friend and Eric Schott recognized that no single company's R&D labs, no matter how smart and well-funded, have the same kind of capability as the crowd. So Sage seeks to promote innovations in personalized medicine by enabling what it calls a community-based approach to scientific inquiries and discoveries. As Wilbanks likes to say, he likes making it easy to share things. Now, this is easier said than done. Sage's mission goes against the grain of the standard business model in both academic science and the biopharmaceutical industry. The questions that Wilbanks wrestles with every day are of crucial importance to anyone who cares about how science gets done, how quickly progress gets made, how people get rewarded for advancing a field. This conversation is a look at some big picture ideas that are relevant to everyone in the biomedical research enterprise. I think you'll enjoy it. Okay, now for a few plugs. Life Science Cares is a collective effort of the life science industry to end poverty in the greater Boston area. Now working with more than 150 companies, Life Science Cares harnesses the industry's human and financial resources to support service organizations doing the very best work in the areas of basic human survival, education, and economic sustainability. To learn more about how your organization become a member or how you can volunteer, visit www.lifesciencecares.org. You may also want to listen to an earlier Long Run podcast that I did with Life Science Cares founder Rob Perez to hear him describe the mission of this group. Also, if you enjoy listening to these in-depth interviews, you'll love reading Timmerman Report. You can subscribe to Timmerman Report for $149 a year per person. Group subscriptions, which include an internal sharing license, are available at a discount. For details, ask me at luke.timmerman@protonmail.com. Now, join me and John Wilbanks for The Long Run. So with me today is John Wilbanks. He's the Chief Commons Officer of Sage Bionetworks. We're sitting here in Seattle, not too far from the Space Needle, at some new digs Sage has. Welcome. Thanks for joining me on the show today, John.
Thanks for having me.
So let's start from the very beginning. Commons Officer at Sage Bionetworks. Just real quick, what do you do?
The short version is I try to make it easy to share things.
Well, that sounds nice.
Sometimes.
Harder to do, easy to say, hard to do.
Yeah, that's the idea. The long version is that we try to apply a lot of the ideas that Elinor Ostrom laid out in her career as a Nobel-winning economist about how resource systems operate, how things get shared, how communities work together, and how these sort of commons-based resources and common pool resources can lead to more innovative ecosystems. And she did this work in the natural world, but we see a lot of analogs to it in the digital world, especially in the science world, because in the same way that ecosystems have to lead to crops coming out, right? Science knowledge systems have to lead to knowledge coming out. And so my job is to try to build a group and help that group move towards being able to bring data in, either from scientists or directly from non-scientists, study participants and so forth, and then ways to share that data back out to scientific communities so that they can use it to generate new knowledge.
Okay, this is really hard stuff for us in biomedicine, healthcare. We don't like to share data. All of the incentives are pointing the other direction. So this is a real uphill battle. Let's get into, we'll get into more of the specifics of how you're going about this later, but I want to peel it all the way back to the very beginning, a little bit about yourself and who you are and where you come from. So where did you grow up?
I grew up an academic brat. So I was born in upstate New York, and we moved to the former Yugoslavia for a while, and then settled in East Tennessee, which is where I went, from kindergarten all through high school, and where my family still is. My dad was a climate scientist at the Oak Ridge National Laboratory. So I grew up around scientists but mainly physicists and climate scientists. And my dad specialized in sustainable development before it was really a phrase. And so I also grew up being his library rat. He didn't really love the library at the lab, so I would go with him to the library at the University of Tennessee and learned how to locate information. It's where I got exposed to connected digital systems. And then from there, I went to college in Tulane in New Orleans. Studied philosophy with a year in France, studying French at the Sorbonne. That's where I come from, more or less.
Why philosophy?
I started out in molecular biology, but I really hated my teacher. and I'd applied to college as a science major. And when I got to Tulane, you had to take balanced course loads. And so my freshman year, first semester, I took an intro to philosophy course. And I had a great teacher, Professor Thomas, and something about it just really called me. I really enjoyed it way more than, biology at that point was really taught as a memorization exercise. Yep. And then I had this philosophy course, which was a thinking exercise, and that was just more fun. And so, Tulane's in New Orleans, and so during Mardi Gras, my freshman year, I walked into the dean's office on a whim and changed my major.
Now, this was early 90s, so biology...
90 to 94, yeah.
Biology, I guess people may have been talking about the Human Genome Project, but not really. I mean, it wasn't... But biology was more of a rote memorization kind of area. It wasn't like the hot thing to be studying.
That's right. It was sort of the closing of the window of the time before computing and sequencing hit culture, much less science, right? I mean, I had an email address, but I had to walk to the computer lab to use it. I remember getting an ATM card for the first time during my sophomore year, right? And so the idea that biology would be computational was not part of the curriculum, shall we say.
Yeah. Did you develop a crush on a favorite philosopher?
I liked John Dewey a lot, and sort of the early 1900s humanists really spoke to me a lot. But what I really liked were the ancient Greeks, like the pre-Socratics, Anaximander and some of the others, because it was almost like reading poetry. And I was really interested in the fact that philosophy changed radically when the Greeks and the Egyptians got together and math entered Greece, right? But that's more of a history play than a philosophy play. It turned out I didn't really like doing philosophy. I enjoyed sort of the practice of reading philosophy and talking about it, which is why I didn't wind up going to graduate school.
You did end up going to Capitol Hill, right? Working for Pete Stark.
Yep. I wound up that. It took me about a year and a half after I got to D.C. to get to the Hill. So I'd been a cook in New Orleans. I'd been a tennis pro during the summers. During college, and you remember what it's like. Everyone's, what are you going to do when you graduate? And I had no answer. Like everyone else I knew seemed to have an internship somewhere, and they'd had summer experiences, and I had been off having fun and boiling crawfish in a blues club.
Companies don't exactly come to campus to recruit philosophy majors
who have been cooks, right? Like it's the stereotype is the old joke is, what does a philosophy major say after graduation? It's, do you want fries with that, right? And so I got tired of answering the "what are you going to do when you graduate" question. I just started saying I'm going to go to D.C. I had one of my old friends live there. He was graduating from Georgetown, so I knew I could crash. We graduated faster than they did, so I knew I could crash for a couple of weeks there. And I sort of had this faith that I could grind out a job because of the turnover in D.C., because D.C. is a very seasonal town as, elections change. And this is 1994. I'm a Democrat from the South. There were a lot of Southern Democrats in the summer of 94. It was the summer of health care under Clinton. And so I kind of thought that I would be able to hook on pretty quickly if I went there. And so I went to D.C. and I made, I think, 350 or so phone calls to campaign offices and nonprofits in the white pages of the actual phone book. and got an internship for Ted Kennedy's campaign against Mitt Romney. Worked there for several weeks and got a job at the Democratic National Committee. And on my third day, I was laid off. And this was all of the dysfunction that led to the Republican takeover in '94. That wave was hitting the DNC in the summer. And so I got hired and laid off in a 3-day period as part of that dysfunction. And so I scuffled for a while, and I got a job answering the phones at the Political Action Committee for the Physical Therapy Association. And while I was there, I got exposed to the Stark 1 and Stark 2, Medicare reimbursement laws, some of the work that was going on around in healthcare policy. And we worked a lot with Pete Stark's office because he believed in using physical therapy and occupational therapy to lower Medicare and Medicaid costs and extend Medicare and Medicaid to more populations. And when an opening came up for a sort of an outfielder legislative assistant, I applied for it and got it.
Huh. Now, what was the big takeaway from that experience? Because it seems to be an important one for you.
I learned a lot about the way Congress actually works. I was only there for a year and a half or so. It was a hard job. But the biggest thing for me is that there was a web server and a constituent mail server. There was a web server at the Physical Therapy Association, which was my first exposure to the World Wide Web. It was the first web page I ever wrote, although I don't think it ever made it to the internet. But it was the first time I ever wrote in HTML. And then when I was working for Pete, constituent mail server would go down, and there was one woman who could fix it, and she taught me how to fix it. And so suddenly I knew a little bit about databases and mail merges. And then I worked, I built more web pages during that time period. I got my first internet account. And so for me, there was this incredible, intense 1-year graduate program in the reality of federal policymaking. But also it was really my first exposure to creating things with technology.
Uh-huh. So this is the mid-90s. Internet is starting to gain steam, but we're not yet in the full-blown .com boom.
I still had to use WinSock, if you remember WinSock.
No, I don't.
Yeah, it was that's the thing you had to have on your computer to connect to the internet in the early days, right? If you wanted to run your own domain, you had to set up a zone file, right? There were no sort of registrars and ISPs the way that we think about them. I helped Congressman Stark get a web page up for his campaign. I did this, on the weekend as a volunteer, as one does. And the ISP was called Hermes, right? And when he first saw the charge, he was convinced I had gone to Hermes and bought a scarf for my girlfriend, right? Because he didn't know what the letters ISP meant after that.
Yeah. So we're talking way back here.
Yeah.
Now,
this is like right around the Netscape IPO. I remember the first time I saw the Netscape browser, and that was probably when I was at the Physical Therapy Association. Yeah.
So that's, it's starting to, capture some popular attention. You got interested. You went, now, I don't want to walk through your whole resume, but I did see that you went to the Berkman Center for the Internet and Society at Harvard. This would have been during that .com period, late 90s to early 2000.
Yeah. So 97 is when I left the Hill and moved to Boston, fell in love with a girl. And so for the first year I was up there, I actually was consulting for a company called Phonics, Pen Voice Interaction. So this was, I was in the stacks at the MIT libraries, which were open. They didn't require an ID. And I was researching all sorts of computer-human interaction theories around using voice commands, pen commands, early clamshell tablets. And that was a lot of fun. But then they opened an office, and the office was up in Woburn. And I don't know if you know Boston, but I went from working at home in Somerville and going to MIT to like a 3-bus connection up to Woburn. And so I didn't like that very much. I was having to do a lot of networking, hand cabling, Ethernet cables, and RJ45 connectors. And so there's this annual thing called the Big Help in Boston, which is a big, fat newspaper full of job ads, or it was in the late 90s, right? Mm-hmm. And I saw this ad for the Berkman Center. And they were looking for someone that appeared to have either a PhD or a JD or both and had run a university for an assistant director ad. And I was like, well, I'm going to throw out 100 resumes. I'll throw in 101. And but I realized that you could apply by email. And so I had internet at home, which was not that normal. I had a computer at home, which was not that sort of normal at that point. And I think that's what got my resume up to the pile, because I was like 25.
Young guy who's like a little more tech savvy than the average bear.
It has some policy background, right? Coming off of the Hill, little bit of policy, a little bit of tech, showing a little bit of system hacking to track down an email and send it. And so I was fortunate, right? They took a look at my resume, and Jonathan Zittrain and Charlie Nesson were willing to take a flyer on me.
And what did you learn there?
A lot of admin stuff, a lot of managing stuff. So as the assistant director, I didn't have a lot of policy sway, nor did I deserve it, right? I was walking in off the street, and these are Harvard professors. But so they wanted me to do things like get the budget in line. And so I had to learn how to deal with the dean of finance at Harvard Law School, who would say things like, "Why are you running on actuals instead of a budget?" Right? And because it was the dot-com boom, the endowment units kept doubling every year, and so the cash kept looking like it wasn't going down. But that was because the endowment kept doubling, and we were still spending, right? And so I learned how to start thinking about fundraising and development. We hired a bunch of law students and undergraduate students. Many of them are very famous now. And so I learned how to, keep their pay sheets in line. And, we had OSHA violations because we had law students sleeping in the hallways because they were writing code at night while they were going to school during the day. And I had to learn how to deal with things like that. And so that was sort of that was the blocking and tackling of my job, right? Learned a lot about things like video casting and real-time chat because we were broadcasting the ICANN meetings from wherever they were in the world. And I got to work on that, which was great. And then at the higher level, I got to sort of be in the room when insanely smart people were working on really core internet policy issues, like handing over the domain name system, right, to ICANN, or some early questions, deep questions about copyright and intellectual property in the internet. And so I sort of, through osmosis, I started to pick up some of the policy issues while I was there. But most of what I did was really, you're the manager.
Uh-huh. And did you look around and think at any point, gee, why are all these other people getting rich?
I didn't know that many of the people. So I didn't have a lot of friends who were doing tech. And so I didn't know a lot of the people getting IPOs, right? I think that was more Silicon Valley.
Yeah.
And what I did see is that my girlfriend was a scientist. And she worked at a company that got bought by Millennium. So she worked at LucasSite, which then got bought by Millennium.
Yeah.
So I remember going to the Millennium holiday party in maybe 98 going into 99, and there, champagne fountains and Gladys Knight and the Pips. And it was crazy.
Uh-huh.
And I remember thinking, I just can't believe how much money is sloshing around. But it wasn't, why are these people getting rich? That's just, I didn't see that many of those people. I was kind of lucky in that all the really good technology people already had jobs. And so they were hiring people who could learn technology, and that was me. But you say that Boston wasn't quite that way.
Okay, so how did this bundling of interests? I can see things are coming together for you now at this point. How did it morph into life sciences, genomics?
Well, one of the guys who's one of the law students at HLS, Antoon Nabhan, was a good friend of mine, still is, and he spent a summer out in Silicon Valley doing one of these summer associateships, and came back having seen the VC land and the froth, and I had been hanging out at the labs at LucasSite and sort of asking questions like, "What's that?" "That's a flow-assisted cell sorter." And, "What's that?" It's an Affymetrix microarray machine. And the Affy microarray machines, right, the gene expression stuff fascinated me because I'd had just enough biology to sort of understand what was going on.
Uh-huh.
But the idea that you would have these light brights that would show you if genes were up or down and how much, and was really interesting to me. And I had, because of the stuff at Phonics, I'd done a little bit of work on acoustic algorithms, noise defeating systems, because you have to figure out, like we're talking, what are the words and what's the street noise from, Belltown in Seattle. And so I, was hanging out and I would ask people, like, how do you analyze that data? And they were using algorithms that looked a lot like the algorithms we had used to do voice recognition. And one of the problems I had mentally with voice recognition was that it was not semantic, right? You were just sort of doing, statistical recognition. And my senior thesis in philosophy was on epistemology and semantics. And so I'd say things like, don't genes do stuff? Don't you want to sort of account for what the gene does when you analyze the microarray? And they'd be like, yeah, we don't know how to do that. And so I'd been sort of playing around with what would it look like if you had semantic representation for what the genes did that you added to the statistical representations to do microarray analysis. And, Antoon came back, we would hang out, right? We would drink coffee, we would drink beer, we would eat sushi. And before I knew it, we'd written a business plan. And, one of the people who sat in the hallway said, hey, you should talk to my dad. He's an investor. And the next thing you know, like it being the late 90s, like literally, this is the thing about sort of privilege and systems is if you're sitting at Harvard and you have that kind of idea, like you can just be kind of talking bullshit and someone will show up and give you a check, right? And I don't want to exaggerate it, but it wasn't that far, right? I had like 3 meetings and suddenly I was the CEO of a startup company.
And now it's like, okay, I really got to do something.
Yeah, it's oh shit, right? Like, so we started a company built around the idea that you could add in semantics to represent the knowledge and make the knowledge computationally interoperable, and that you could use that to do array data interpretation. And right around the time we started, and we got about $750,000 in an angel round. And right around the time that we were on the edge of getting to market, like 5 or 6 open source software packages for array analysis flooded the market. And so we pivoted, we sort of focused on the semantic aspects, realized pretty quickly that it didn't matter how good your knowledge architecture was. There wasn't enough knowledge to architect to have anything successful, right? It's an echo of what we'll talk about for today, which is that the biological complexity is so vast that even really good knowledge architecture just illustrates how little you know. And so we started using the tech for database integration, back-end sort of knowledge management, which is what worked, right? So we had some good tech for synonym disambiguation. So P53 has, more than 90 synonyms, or it did then. And you'd have files attached or knowledge attached to each synonym, but one query wouldn't resolve them all. And so we sold that to biotech and pharma companies, and
you could sell it because there was no free open source alternative.
Right. There was no free open source alternative. And we were actually building this all out of open data. We were building off the NCBI databases. What we would do is take them and then basically integrate them all into one big semantic graph, right? And this is in like 2003. This is way before there was graph stuff available from Amazon or anybody. So we had to build our own grid in a closet about the size of the room that we're sitting in now. And that grid had to run for 25 consecutive days to build the graph. We only built it a few times, I think over 3 years. But what it was good for was backend, right? It would let you sort of query one synonym and get all the data related to all of the synonyms. And that was the utility that it had. But, this is, by 2002, this is what we're doing. And by 2003, like half of our customer pipeline's going out of business.
That was a downswing.
Yeah.
In the
and it was
biotech
So
the
if you were a
post-genomics
vendor,
hangover was going on then. People said, wait a minute, we were supposed to get cures magically. Now that we've got the human genome sequenced, where are all the cures? Well,
this is a pattern.
Yes.
This is a pattern we're going to see, right? And the customer pipeline started to dry up, even though we were having success. And so our investors, had gotten in. Our venture investors had gotten in because the idea was that bioinformatics would get you biotech returns at software prices. And once that became evident that it wasn't going to be true, that the vendors to biotech were having a worse crash than biotech.
Yeah.
And so they started putting us up for sale, and we wound up merging with another small company called Genstruct up in Boston, which did sort of small world modeling. You would take a bunch of observed molecular changes and then use the literature and the data to annotate it, and then you would say, what are the most plausible explanations for the changes based on the small world of knowledge? And so we sold it to them. We didn't make any money. But we had sort of an honorable exit, and I spent a year there with those guys, and I just kind of figured out that I was probably not meant to be a startup entrepreneur.
Why is that?
It's a hard job, and it's hard to raise money and spend money and build value. It's even harder to get the check back with another zero on it, and there's a certain piece of that just didn't really appeal to me. I loved a lot of the things about it, but I didn't like, honestly, the privatization of it was hard for me because it's not my instinct. I sort of, there's a reason I went into government, and there's a reason I've worked in nonprofit and academia so much. And although it was a great experience, the entrepreneurs who wind up making money for their investors have a degree of obsession with returning value that just wasn't there for me. I wanted to create value, but it's the obsession with capturing value is what distinguishes a lot of the really successful entrepreneurs from the less successful.
Yeah. Journalists can relate.
Yeah.
Creating value, capturing it is the harder part.
Yeah, and you've got to be obsessed with capturing it because the good ones capture almost all of it.
Yes. So you decide you want to create value, and you become an open source guy.
Yeah.
Was this when you went to Creative Commons?
Well, I spent sort of a year between that at the Web Consortium, working on the Semantic Web team for Tim Berners-Lee, helping start the Semantic Web for Life Sciences project. So there's Eric Newman, who had actually, when he was at Beyond Genomics, was my first customer at my company. And he was helping get this off the ground. Andy Palmer, who was at Infinity Pharmaceuticals, Eric Miller at the Web Consortium, Danny Weitzner. They were looking around and saying, if this works from a knowledge management perspective on the back end for pharma and life sciences, maybe this is a place to get new members into the World Wide Web Consortium to care about the web. And it was the early days of semantic web when everyone thought it was going to sort of, be everybody's new bicycle. And so I spent a year there sort of helping recruit some companies to come to workshops, helping stand up a working group. And during that was when Creative Commons decided they wanted to start a science project, found some money. And I knew everybody because Creative Commons has started at Berkman. Right around the time I was leaving Berkman was when the Eldred versus Reno decision, Eldred versus Ashcroft decision came down. And Creative Commons was sort of born out of the ashes of that Supreme Court decision. And so I knew a lot of the people involved. I knew them on a personal level. I knew them on a professional level. And it was just a really fun opportunity to go back and work with people who I loved and work on something that seemed like it took what I had been doing but let me do it in a business model that made me feel better and was more fun.
And what was the business model?
Nonprofit, right? It was nonprofit advocacy, really. But Creative Commons is fundamentally has always been a product organization, which is not traditional nonprofit. Right? They say the traditional nonprofit would say you should license your copyrights openly, and Creative Commons is like, here are licenses that you can use to do that. They are machine readable. They are human readable. And it was a really interesting. It was always fascinating to me the way that worked, and so. The idea that we could take that concept into the sciences and say, all right, like where are all the places where sharing might help? And so, and the original sort of grant was looking at, patent thickets and patent licensing and patent pools, but also at things like biological materials, right? Databases, open access to the scientific literature. And so it just seemed like, I had interacted with all of those things at my company, right? Except for the actual biological materials, right? But we had dealt with patent thickets, right? We had dealt with trying to integrate, the hundreds and hundreds of open databases and make them usable. I had seen how easy it would be to privatize the integration layer, right? Because if you could imagine, if you had the open databases, but somebody privatized the integration layer and then patented it, you would really hamstring the utility of the open databases. We had been at the company that bought us. We had to for every time we built one of these small world semantic models, we ran into paywalls for the literature. So I had seen firsthand all of the places where a good entrepreneur gets beaten back by the fact that the knowledge commons of the life sciences was badly structured.
You run into other people's business models, which
That's right.
will fight very hard to defend.
That's right. So I was really interested in the idea of, so much of the life sciences knowledge space is pre-competitive because you make your money on the intervention, which is not knowledge. It's, a physical thing, right? It's a drug. At that time, a small molecule, right? So it seemed like there was this room to run where you could say, well, maybe we can really rethink the whole sort of life science knowledge space as a commons. And the org really gave me a lot of freedom to play around in that space. And so we built up this other wing of the org. We built it up in Boston. The org was in San Francisco, and MIT gave us a home inside the computer science and AI lab.
Oh, so you were in Boston all this time?
Yeah.
Okay.
And so the project on math and computation at MIT's computer science lab gave us a home. And so this is where, Richard Stallman lives to this day, is in that laboratory. A lot of, it goes back to the 50s. It was this wonderful, intellectual lineage of computing and open source and science. And so it was this incredible sort of place to hang out and work. And so we grew and we ran that for a while. And we actually recapitulated some of that database integration technology using open source semantic web approaches. We did a lot of work on being an advocate for open access to the literature, but mainly so that you could build search engines and do, more accurate processing and text mining of the literature. We did a massive project on materials transfer agreements that no one ever used. It was a great project, but we ran straight into the incentive problem that no one was going to share what was in their fridge, right? We did a patent licensing project with Nike that erupted in sustainable technology sharing. But in the end, it started to get obvious to me that advocacy and even product advocacy in the sciences only goes so far. And if you really want to create change, you've got to join a science organization and, develop a multi-year approach to say, are we going to actually implement these things and will they be better or not?
If you enjoy listening to these interviews with biotech newsmakers, you'll love reading Timmerman Report, my subscription publication. You can subscribe to Timmerman Report for $149 a year per person. More than 60 pharma companies and universities have gotten group sharing licenses. For details on a group subscription, ask me at luke.timmerman@protonmail.com. And Life Science Cares is a collective effort of the life science industry to end poverty in the greater Boston area. Now working with more than 150 companies, Life Science Cares harnesses the industry's human and financial resources to support service organizations doing the very best work in the areas of basic human survival, education, and economic sustainability. To learn more about how your organization become a member or how you can volunteer, visit www.lifesciencecares.org. Lastly, are you planning a conference, a team-building event, or a leadership retreat? I've developed a presentation based on my Mount Everest summit expedition earlier this year. I'm sharing this experience over the coming year through a select number of company talks. These Everest talks feature gorgeous photos from the world's highest mountain, along with lessons on leadership, teamwork, and what it takes to overcome adversity to achieve the really big goals in life. Interested? Ask me about an Everest talk at luke.timmerman@protonmail.com. Well, there are so many layers to the problem to get to where you want to go. I mean, with biological data, there's the lack of reproducibility, there's the publication bias, there's the fact that grants are not given to people for putting raw data. Nobody puts their raw data out in, unless they really have to.
Right.
There's business models like, pharmaceutical companies have their patents. They're not incentivized to put things out in the open. I mean, so you become aware of this over time. It sounds like at this point in the game, you get all this stuff. And then you meet the crew from Sage. Right.
Well, so the other piece of this, though, is that pharma actually supports a fair amount of biological sharing. Right? So like HapMap, a lot of that funding came from pharma. Structural Genomics Consortium, that money's coming from pharma because the more open the biological space is, the less money they have to spend doing biology. And they recognize that as a collective good. So there's these interesting places where you can intervene, right? But it's not the intervention that you thought it was. And the real disruption comes from the people who build HapMap, who build the Structural Genomics Consortium.
Do they have funding? Do they have incentives to do so?
Well, but it's because they're in the arena. If you're sitting on the side telling people what to do, right, then everyone's incentives sort of grab them. But if you jump in and actually say, we're going to do the science this way, and we're going to show you that it's better, then that's where you can actually really get there, right? Because we had some good successes. We got, at any rate. But yeah, so it's 2009 at this point, right? Obama is in office. There's sort of the beginning of a wave of open policy because Obama came in and all these people that I knew from Berkman start working for Obama, right? Obama starts putting Creative Commons licenses on his photographs during his first inauguration speech, right?
Anybody can take them, use them, spread them widely.
And just like the semiotics of that, right? Having a president who sort of comes in and gets digital enough to use open licenses, right? And it's and after a really long period of advocacy in the open access movement, you've got this swell, right, of people doing policy work around access to the scholarly literature, right? And I joined late in that, right? I'm far from an early OG in that field, but and you've got a lot of people looking at Wikipedia because Wikipedia became ascendant during those 6 years, because I remember when Wikipedia was fringy, and by 2009 it was a model, right?
Social media too. Twitter and Facebook were taking
just
off.
Getting started. That's right. I had just joined, I think, both of them around then.
Yeah.
And so Stephen Friend, I get a call that Stephen Friend wants to see me, and I of course knew who he was because all of my investors back in the startup I was like, why can't you make as much money as Stephen Friend did? And I'd be like, because he's an MD PhD who was one of the first people to clone a cancer gene. Right? He's actually a scientist, right? And so I knew who he was, and I was kind of intimidated. And so I call him back and I say, here's where my office is. And he walks in. And
now, for those who don't know, Stephen Friend had started a company called Rosetta Informatics here in Seattle, actually, that captured gene expression data, had some bioinformatics going on, sold this company to Merck in 2001, I believe, for like $600 million. So very successful entrepreneur. He went on to stay at Merck and ran their cancer research group there for a number of years, but then he got the itch to kind of branch outside the walls of Merck.
Right. And I won't speak for Stephen, right? But one of the things that he was dealing with was the problem of biological complexity. And so I think one of the reasons why we keep thinking that a new technology or a new approach is going to save us is that we keep getting defeated by biological complexity, and we want the new tech to be the savior, or the open approach or whatever to be the savior. And so Stephen had been building these big data sets of what he called global coherent data, which is where you had the sequence of the organism, you had some clinical data about the organism, you had the outcome of the organism. And if you put those things together and used sort of early ML and AI, you could start to get much closer to causality in biology.
Genotype through phenotype.
It's the same story.
Integrate all these records that don't necessarily exist in the same place, put it together to tell a more coherent story.
That's right.
But one of the things we learn is that the underlying data, the genes, are not deterministic. Biology is more complicated than we originally thought, as you said.
Right, and context matters, right? Context matters. The context the organism is in matters a lot, right? So he had made a pitch to Merck to sort of build a Wikipedia of this sort of global coherent data and share it. And so we actually, I think, we still have that presentation. It used to be on our website. It probably fell off when we built our new one, but we've got to make that available. We actually have the presentation he gave, and it was on there. It used to be on our website. And Merck's reaction was like, pass, right? We're not going to do that. But what they allowed him to do was to take the Rosetta unit out, a chunk of the Rosetta unit out of Merck, and spin it back into a nonprofit whose mission was to create this Wikipedia of global coherent data and make it openly available. And so, he had gotten wind of my name as someone who knew how to do weird sharing things. Walks into my office, we spend what's supposed to be a half an hour, turns into 2 hours, and we just connected. We clicked. A week later, I was out here in Seattle meeting Eric Schott, who was his co-founder at Rosetta, getting my tires kicked by their team to see if they wanted me involved. And I joined the board. Before it was even named, I joined the board of directors. And, for a couple, and so that was really the story for a couple of years. I served as a director. I came out here maybe quarterly. I spent a lot of time on the phone with Stephen. And then the more I saw of it, the more I realized that if I wanted to actually see whether or not what I was saying was true, I needed to join a science organization. Here was a science organization that wanted to work with me.
What were you trying to find out was true?
Does this sort of collaborative data sharing, right? Does that actually make science better, right? And what does better mean? Does better mean faster? Does better mean more? To what degree of more? Are we talking about orders of magnitude accelerations? Are we talking about orders of magnitude increases in the number of discoveries you can make? Going back to Ostrom and sort of this ecosystem is, what's the carrying capacity of data, right? We know the carrying capacity of a field, right? If you grow wheat in the field one year, you can grow wheat in it the next year. But if you grow in it every year, you exhaust the field, right? Is data like that, or is data more like a tree, where if you burn the tree, what you're left with is charcoal, and you can still burn charcoal, but you don't get as much heat as you did out of the tree, right? Or is it like fruit and it's just evergreen? Like nobody knew this. Everyone has ideas, but nobody knew it.
Well, and having covered the story of Sage's founding, I'm dating myself here. I did talk with Stephen and Eric.
I remember. That's when we first met.
Yeah. And I remember him being enamored with the way physicists shared their data in a more continuous, centralized repository sort of way. Why can't biology do something similar, at least in some respects? I mean, having come from Merck, he understood the need to have intellectual property around your composition of matter, say. But there were certain things that weren't appropriate to share. Mm-hmm. But a lot of things were, and just weren't being shared because of, this is the way we've always done it. Cultural inertia, or people just not really thinking it through in a long-term way. But he also fell for this presentation. I believe it was from Jim Gray at Microsoft Research, what he called the fourth paradigm.
That's right.
A new way that science could be done that wasn't going to start with a hypothesis that would, basically there would be continuous data capture and analysis, and it would throw off all kinds of new hypotheses, right? But why don't you explain that thinking?
Yeah, so Jim was a fascinating guy. He disappeared at sea right after he gave that talk. Like 2 weeks after that, he sailed off through the San Francisco gate for a day trip. He was a very experienced sailor, and he never came back. And I was supposed to meet him like a month later to try to see if I could get him onto my advisory board at Science Commons. But he really influenced me because as Stephen as well, because he sort of saw the future of where cloud was going. And so I'd been this big semantic web guy, and then cloud pops in and makes statistics at scale workable in a way they hadn't been. It also made graph computing possible at scale in a way that it hadn't been. And so Jim was able to look at those earliest days of it, and this is, 08 maybe, and see that you were going to go to a world where the data was too big to download. Right, which
you wouldn't have it on your hard drive,
which messes with open, right? Because open data depends on the concept that people are going to download it, right? But it wasn't going to be on a hard; it was going to be too big, right? Again, 80 terabytes of BAM files, is a lot of money for the cloud provider to pay for the transfer of, so that the code was going to have to go to the data, right? Jim saw both of those elements, right? He saw the beginning that data would be so big that you would put your code into the data to tell you what was the possibility space. What are the hypotheses that are available to you given the data? He talked about, don't build a complex data system this way by building a complex data system. Go from working query to working query. Start with 20 queries that have to compile, and then do 20 more that don't break the previous 20. And if you do that, you're going to wind up with a data network in the cloud that is successful. But if you start by saying, let's build a data network, you'll fail, right? was brilliant, really. And so Sage, in a lot of ways, built towards that from the beginning. So like our technology has been built towards the cloud, right, from a very early day. Our science has built towards this idea of bringing the code to the data from a very early day. And in many ways, that original version of a Wikipedia has evolved much closer to Jim Gray's vision than Jimmy Wales's vision. Right? So Jimmy Wales founded Wikipedia, but we've wound up at something that looks way more like Jim Gray than Jimmy Wales.
How so?
So, I mean, we run these challenges where the data, you have 750,000 medical images. They weren't consented for sharing. We can't make them downloadable legally because of privacy reasons. Nor could we afford to make them downloadable because we, as the people who pay Amazon for our cloud fees, would have to pay for the transfer costs. Or we'd have to charge the user. And so, what user's going to put up 10 grand to download the database? And it would take days, right? It's a different paradigm. So to run a computational interpretation challenge, for example, we've got to basically do what Jim Gray said more than 10 years ago and let people bring their code to the data, keep it in a container on the web, and give them a set of queries that they can run in the data. I mean, it's exactly what Jim laid out all those years ago. And here we are in 2018, and it's the state of the art of what we do.
It is, but it still runs into some cultural headwinds. I think particularly in Silicon Valley engineering culture, this reminds me of when you and I just a couple weeks ago were at the Biden Cancer Summit. You made a remark at a data sharing breakout session where I was at about how you can't just take one big data set and merge it together with another big data set and magically think cures will come out. Because big data just doesn't work that way here in biology. It has to align properly. But that mindset you find quite prevalent. I've seen this myself many times that in tech audiences where all we need is more data. More data will give us the answer, and it's just not. You had an example of the Merck database on gene expression, which is a huge and rich set of data that Sage was founded with. But it hasn't been used.
Right.
And it doesn't neatly merge, I would imagine, with other data sets that are considered relevant by biologists today.
Right.
So it's there, but nobody's using it.
Yeah, and that's an issue, right? And it's hard because there is a world in which if you merged a bunch of data together, it would be super useful to lots of people. But the reality right now is there are not that many scientists capable of interrogating big databases using machine learning. And so for some of those people, like for a guy like Atul Butte, who's a brilliant scientist, and I've known him for a long time, right? Atul can take a bunch of public databases and mash them together and get insights out of them. I don't know if he can get cures out of them, but he can get good insights out of them, meaningful insights, patient meaningful insights. But there's not that many Atuls right now. And so one part of the problem is we need more Atuls. We need to teach scientists to be more like that, to think more like Jim Gray would say, to go, send your code to the data and have it kick out hypotheses. But a big part of this is that we can generate a much larger pool of scientists by the way that we generate the data. And so if we generate data towards a construct of hypothesis exploratory research instead of hypothesis driven research, which is, I think A causes B, I would say is hypothesis driven research. And I only generate data to see if that's a true hypothesis. We can generate these big databases that let you say, show me all the potential relationships between A and B, right? But if we don't generate towards that construct, it's going to be really hard for the scientists to come in and do that. We're going to reduce the number of people who can make that query. And then there are these other things that normal scientists do, which are sort of more low-hanging fruit, which would be things like meta-analysis. I've got a small sample size because I got a small grant, but I have a bunch of sequence data, a bunch of tumor sequence data. If I can get other tumor sequence data that was generated the same way from other places, I can drastically increase my sample size. That's doable, right? But it's engineering these shared data resources toward the scientific construct instead of doing it as this abstract munging and hoping for success.
Yeah, I think the phrase you used is the field of dreams.
Yeah.
That doesn't work.
It doesn't work very well.
And
right?
for those who are unfamiliar, this is a pop culture reference to the movie.
Again, an old one.
We're dating ourselves. But if you build it, they will come. And it will be magical.
Right. And this is where, and again, in the background of all of this is the open access to the literature movement having an enormous amount of policy success and beginning to connect open data to it. That's all happening through the early parts of this decade in the 20-teens is a growing movement to push the Obama administration to open up scholarly literature and taxpayer-funded data. And so what you have now is we do have a lot of policy now that sort of says if you got taxpayer money, you have to file a data sharing plan. And you have an enormous amount of success around, true open data, municipal open data, arrests, water, air, legislative works, right? And then there's this sort of divergence between open data like that's useful as it is, right? Because it's connected to GPS or the census. It's easy to integrate. There's lots of users. It's small. You can download it. And then this gigantic life sciences data that is endlessly complex, requires lots of tacit knowledge to use, has all of these privacy and intellectual property constraints that touch on it. And so we have the same policy applying to both. And so the field of dreams problem in the life sciences is that we're not training cadres of scientists to use this data, nor are we building these shared data resources toward a scientific construct. And that is just limiting their utility, right? Because your average scientist is worried about her R01 grant from NIH, right? And R01 is the traditional sort of early career investigator grant. And if you get one and you succeed, you got a good shot at tenure. If you get one and fail, you don't, right? And so I'm worried if I'm that woman running the lab, I'm worried about nailing my R01. So the question is, what can that shared data do to help my R01? Not, I'm going to go burn 6 months exploring that public database and not work on my R01. And so you're back to this incentive mismatch. And it's not an IP mismatch or an anti-sharing mismatch. It's, I've got to nail that grant to the wall. And so going and exploring and doing Jim Gray stuff in that data takes me away from this very reductionist grant that I got funded.
Right. And then you got to get your publication.
That's right.
And you get your publication not by putting your findings out there before publication. You don't give away your scoops.
Right. And then after you publish, right, then the policy kicks in and says, now you need to share the data from that. But, at that point, the publication often comes out after the postdoc who worked on it has left the lab. And nobody there really understands the data well enough to mark it up, right, to make that tacit knowledge explicit knowledge so that, Luke can come in from the outside and use that data effectively because it hasn't been shared towards a scientific construct.
But you guys, one thing that you said that I think resonated there at the Biden Cancer Summit was starting with the query. Sort of like basic customer relations, really. What do the scientists want to know? And can we build a set of data? Can we compile it somehow and put it out there in a way that's relevant and accessible for their scientific questions of the moment? Right.
So this is Jim Gray 101, right? What are the classes of queries? Right. So Jim's sort of theory is give me a specific query. But I think the lesson that we take away from it is what's the class of query, right? Because then you can say, I'm going to go get classes of data for that. And I can keep adding data for that. And so, one class of queries is meta-analysis. Use other people's data to increase the sample size available and the power of the analysis for my data. And that aligns with the incentive of, getting my R01 and succeeding. Another one is triangulating. Right. So if I've got a hypothesis that's coming from genome space about the relationship of these specific variations to health, well, if I can find traces of that in EHR space, it's way more likely to be true than if it's only present in one of the two data streams. And so those are the kinds of classes of queries that you can build towards. And then you can say, we want to keep people depositing data of these classes into these systems, and then they get better and better at serving up meta-analysis and triangulation services. And suddenly people are using shared data resources, and it's not a field of dreams anymore. It's you've got a job to do in your lab, but these data resources out here help you do that job. And then the policy says share your data into those resources, and suddenly we have something that's actually all coherent.
Well, and it sounds like you're making something here, ideally, that will get us to go from this phase of just generating data and dumping data into databases, layering in some context, working your way up the tree from, data to information to knowledge to wisdom, as I think you've said earlier. And that's a long, hard road. I think we're still very much kind of low on the ladder.
Well, this is really about the data to information transform, right?
Yeah.
And I want to also be clear, this is what I'm talking about. I'm talking about reusing data that was generated for traditional science, because that's where there's a field of dreams problem, in my opinion, is the idea that Luke makes data in Luke's lab for Luke's purposes, and that by sharing it, like magic happens, right? And that's where I think sharing towards that query-driven science construct is the answer, not a field of dreams. It's very different to run a project like a Cancer Genome Atlas, right? Or the Accelerating Medicines Partnerships, or the All of Us Research Program, right? And disclosure, we're involved in all of those, so I have a bias in favor of them, obviously. But that's where you're literally generating the data for other people to analyze.
All of Us Research, by the way, seeks to sequence 1 million genomes, NIH-funded program, and it's supposed to be super duper diverse, full picture of America.
That's right, and full EHRs, and a physical exam, and blood, and urine, and wearables, and connecting in social determinants and environmental data. I mean, this is going to be the Framingham cohort for the 21st century, right? Yeah. And so that's an endlessly useful giant database. But it's going to be useful because it's built for other people to analyze. Those of us building it are not going to be the people who are the primary users of it. And so that's where I think you can have a lot of success with a more field of dreamsy approach, because you're not just building it and then they come. Like in Field of Dreams, right? Going back to the movie, they build a baseball field in a cornfield and there's no seats, right? And so it's not particularly likely that people will show up and go to the games at the cornfield, right? But if you got a baseball team in a stadium with beer and hot dogs and child care and all of the modern things at a baseball game, people will come, right? And so there's a big difference between those two approaches. And so we need to have an understanding of data sharing that's nuanced enough to say, well, are we going to be reusing data generated in the course of regular science? And what's the process to make that shareable and useful? Versus we're going to generate public atlases and maps and resources specifically to let other people do work. And both of those approaches can work. The key is to not mix them up.
You started by saying, I like to make it easy to share things.
Yeah, making things easy is hard.
And I think we've made that pretty clear. Your co-leader on that session at the Biden Cancer Summit, Anna Barker from Arizona State, I think she had a great comment, and I'll quote her. She said that data is entropy until it has context. And we want to create information, but we can't do it without context. And we're falling way behind in medicine. And I think the things that you're talking about here are about providing that context, help us move a little further up that ladder toward understanding what all this complex biological data actually means.
And there's some really interesting things emerging now about how that works, right? So take Accelerating Medicines Partnership, which is NIH is working with pharma, right? So it's like half and half funding wise, to look at complex spaces where drugs have been hard to get at, right? So we're involved in the Alzheimer's disease AMP, right? So AMP-AD. And the idea was we're going to fund these labs, they're going to work together, they're going to collaborate, they're going to each take a radically different approach to target discovery in Alzheimer's. And they're going to share data with each other, and they're going to share data with pharma and the NIH. And that's going to lead to these sort of second-order knowledge products that pop out of the open system. And what you see is that that does happen, but in many ways it happens because they're all working on the same tech platform with the same steward, which is Sage, right? So the labs don't wind up making the second-order knowledge product. Sage winds up making the second-order knowledge product. So we have this search engine called Agora that sits on top of AMP-AD, which shows you all of the community evidence for each of the targets that came out of the work, right? Which of those targets have been voted on by the community of scientists as being most likely to be good or bad, right? It's basically a community-ranked wall of targets for Alzheimer's disease with all the evidence and networks around it that you can go in and just search and immediately see if, at your fingertips all the stuff that's available. But it didn't emerge organically. It was something that we had to build as the platform steward. And that's a really fascinating thing because now you can actually fund lead discovery against those targets, right? You start to, so we've made that jump, but it didn't happen organically. It happened because those labs worked in a common technical framework with a common steward, and it was open enough that we could build this interface to it. Because what people really wanted was not the raw data, they wanted the interface to it.
Well, and somebody needs to build it and not just have standards, but adhere to the standards.
Yeah, maintain it.
Yeah. It's not super glamorous in most days, I would imagine.
Right. Well, and think about it. Another element, this is why governance is so interesting to me, is, if you make it open data, then the internet is kind of the governor, right? As long as the file is on the internet, it's available and open and the governance is maintained. And so there's this concept that lots of copies keep stuff safe, right? But if you've got data in a cloud and the company or the nonprofit that runs the cloud goes bankrupt and turns off the servers, it's gone, right? And so it creates this unique importance to think about corporate governance as a really important element of the whole sharing ecosystem. And that's endlessly interesting to me because, we act as this weird mix of platform technology provider because we run, cloud platforms built on Amazon. We're in Seattle, right? We run a collaboration platform. We run a mobile applications platform. We run a challenge platform. But if we were to disappear, right, a lot of things would go dark, right? So what's our corporate obligation as a nonprofit? What's our governance process to do that? We've got we're actually Christine Suver, who leads the team here in Seattle, is on her way to Paris today, right, to give a paper on when you start to do this kind of data sharing, what are the obligations on the organization from a governance perspective?
Yeah, this is a forward-looking question about really, we ought to be asking about the whole internet. Like, if Google got acquired by somebody that wasn't necessarily the same guys that you've trusted these last 20 years, what would that mean?
And you see it in scholarly communication, right? There's all sorts of small, quasi-open service providers in, semantic search of the literature or bookmarking or, social networking. And they're getting bought, right? Elsevier, who is a very smart company, is out there acquiring Mendeley and acquiring other service companies. And so the business model of the organization is really important, right? So, we may run technology platforms. We may also act as a steward. We may also provide scientific consulting services. We might do all three or just one of the three at any given moment. But because we're a nonprofit, we can't be acquired. We have no investors that can force us to be acquired. And so there's another org called Impact Story. They're just up the road in Vancouver. I was on their board for a long time. And they make this, really cool tool called Unpaywall, which is a browser plugin that when you run across a paywalled article, you right-click and it finds you the open version and just gives it to you, right? Elsevier had to do a deal with them because they couldn't buy them.
Uh-huh.
Right? So that's what I'm fascinated by is the role of acting like a company in the sense of doing things companies do, like providing technology platforms and providing consulting services. But then layering onto that, right, stewardship and governance and having a business model that makes it really hard to be captured, right? That's part of what I think makes a stable sharing ecosystem is it may be endlessly complex to us at Sage. And when I talk about it, it makes it endlessly complex. But I can sort of provide a menu and say, like, do you want to make the data downloadable? That's classic open, right? Do you want to make it downloadable but with a data use agreement because there's privacy constraints or consent constraints? We can make that a relatively clean process. Do you want to put it into a container and only allow models to do that? We can offer you that, right? And we're not going to surveil you. We're not going to snoop at your data because we don't need to build models and compete with you. And we're able to do enough of that to be stable enough that we can sort of, rather than proprietize a layer, we can publicize a layer of the research stack.
The average user doesn't want to deal with any of this stuff going on behind the scenes. They want it to be as frictionless, to use the Silicon Valley term, as possible. That's your job, to try to make it easy, like you said at the very beginning. And that will be the test, like in the terms of number of users, number of how much they're using it. That'll be your measurement over time. But last thing, John, before I know we have to wrap up pretty quick, we haven't even talked about artificial intelligence, machine learning. I mean, do you think that there's a point in time when that will rise to the fore and become a lot more useful for analyzing a lot of these shared data sets?
I do. I mean, there's just too much for hypothesis-driven analysis of this. And what ML and AI are really good at is generating patterns, right? And those patterns mapped to the experience of an expert biologist are going to be a very powerful combination, right? And so I do think that that's going to be in the same way that statistics are standard, right? ML and AI are just statistics on steroids, right? And so I think that it's inevitable that you're going to have, classes of scientists coming up who just treat these tools as baseline tools. But because it takes 5 years to get your PhD and another 5 years to do your postdoc, there's a lag in the sciences compared to the non-sciences of how fast tools get picked up. And one of the reasons I'm excited about being involved in TCGA, AMP, all of us, is that they represent, I think, the seed nodes of an open or a shared data network for ML and AI in the sciences, especially all of us, because it's going to be diverse. We've enrolled over 60,000 already. We've got more than 100,000. I think it's more than 100,000 consented. And we're looking at in the vast majority of those come from populations underrepresented in biomedical research. And so these are systems that begin to create both the ability to do large-scale AI in a population, but to do it on a diverse population so that hopefully we prevent some of the preventable failures of biased algorithms that we see from, Amazon's first delivery algorithms didn't deliver to Roxbury in Boston.
Right.
And they didn't look at race, they looked at economics, but economics and race are very tied, right? And so I think that's where this goes, and that's why we spend a lot of time working in those early spaces, is if you can make those shareable enough, open enough, governed well enough, but also diverse enough, right, we can maybe head off some of the problems that we have in culture with AI at the pass in the sciences.
If you put in bad or incomplete data, for starters, you're going to bake in some very serious problems.
That's right.
That are going to be very hard to undo.
That's right, because the algorithms get trained and learn on the first sets of data that they see. And it's much harder to get them to unlearn those patterns than it is to get them to learn the right patterns from the beginning.
You think we're going to see this fourth paradigm, this continuous learning? We're in our mid-40s. Is this going to happen in our lifetime?
I think so. I wrote a piece in the fourth paradigm book, actually, where I agreed with Jim on this whole concept of hypothesis-driven research, but when people think about paradigms, they often think about Kuhn, right? Structure of scientific revolution, where the paradigm sweeps away the old one. And so, for reference, the other three paradigms, I think, were observation theory and simulation, right? And then you will have, hypothesis or data-driven was the fourth one. And I think data-driven doesn't sweep away observation theory and simulation. I think it weaves around all of them. And so you feed observations into it, and theories make it better, and simulations are how you test it. And so I think we're already living in the fourth paradigm. It's just unevenly distributed. And the real task of the next decade is to make it fair, right? Both in the data sense of, fair, but also in the social justice sense of fair. And to make it accessible enough that more scientists use it and that more people become scientists in the same way that, I became a web developer without being a technologist. I think patients ought to be able to ask questions and go from query to query, not just researchers. And so That's to me the task is right now we're building a system for a very elite set of users. And if we can do it right, and we can vastly democratize who those users are.
Well, John, we've talked about a lot of stuff here. Next time we talk, let's talk about how to fix the internet in general.
I can get you somebody else for that. Thank you.
Thanks very much, John. Thanks for being on the show.
My
Long
pleasure.
Run. Thanks for listening to The Long Run, a production of Timmerman Report. Pedro Rosado of Headstepper Media was the producer and editor. Music comes from D.A. Wallach. And thanks for listening. If you're interested in sponsoring the show and getting your name in front of biotech thought leaders, send me an email at luke.timmerman@protonmail.com. See you next episode.